Hello, Accelerated Chemistry students. This is Ms. Christopher, and this is your Chapter 19, Section 1 video notes all over acid-base theories. So acids and bases have very distinct properties. So let's talk about the acid properties first. They're tart or sour tasting. When in aqueous solution, they are either strong or weak electrolytes. They can burn your skin. They react vigorously with metals to make hydrogen gas, have a pH less than 7, and cause indicators to change colors. Bases, on the other hand, have a bitter taste. They feel slippery, can be corrosive. Aqueous solutions of bases are strong or weak electrolytes. They have a pH greater than 7 and can cause indicators to change color. Now we're going to talk about some different people who came up with different theories about what acids and bases were. So Arrhenius came about the idea of acids and bases from looking at acids as being hydrogen-containing compounds that will ionize to yield hydrogen ions in solution. Bases are compounds that yield hydroxide ions in solution. So using his theory, acids vary in the number of hydrogens they contain that can form hydrogen ions. So if we look at some common acids, some of these compounds have one hydrogen, some of them have multiple hydrogen that can form hydrogen ions. So a hydrogen atom that can form a hydrogen ion is described as being ionizable. So nitric acid, HNO3, has one ionizable hydrogen. Nitric acid then is classified as a monoprotic acid. Remember, mono means one, and protic reflects the fact that it will give off a hydrogen ion, which essentially is a proton. Acids that contain two ionizable hydrogens are considered to be diprotic, and acids that contain three ionizable hydrogens are considered to be triprotic. So not all compounds that contain hydrogen are acids. So only a hydrogen that is bonded to a very electronegative element can be released as an ion, and we call those bonds polar bonds. So when a compound that contains such bonds dissolves in water, it's going to release its hydrogen ion, and you can see that happen in the formula for hydrogen chloride down below. So it will form hydrochloric acid. It will give off an H+ ion and then a Cl- ion. In aqueous solutions, hydrogen ions are not present. Instead, the hydrogen ions join up with the water to make hydronium ions. Hydronium ions, or H3O+, is the ion that forms when a water molecule gains a hydrogen ion. Methane is an example of a hydrogen-containing compound that is not an acid. The 4 hydrogen atoms are bound to the central carbon by weak polar bonds. So methane has no ionizable hydrogens and is not an acid. Ethanoic acid, which is commonly called acetic acid, is an example of a molecule that contains hydrogens that do not ionize and hydrogens that do ionize. So the hydrogen that's going to ionize here is the one to the right that's connected to the oxygen. That is going to mean that ethanoic acid is a monoprotic acid because it only gives up that one hydrogen. The 3 hydrogens attached to the carbon atom are weakly polar, so they do not ionize. And so the only one, like I said before, that is going to ionize is the one that's attached to the oxygen. So that's all about Arrhenius acids. So now let's talk about Arrhenius bases. So the table below lists 4 common bases and how their solubility in water is. So sodium potassium hydroxide are soluble. We should remember that from our solubility rules. Any group 1 element is soluble. Calcium hydroxide and magnesium hydroxide are very low soluble in water. So the base sodium hydroxide is known as Li. Sodium hydroxide is an ionic solid, and so it will dissociate into sodium ions in aqueous solution. Potassium hydroxide is another ionic solid, and it dissociates to produce potassium ions and hydroxide ions in solution. So remember, the fact that potassium hydroxide and sodium hydroxide dissociate and produce OH- or hydroxide ions, by Arrhenius's definition, it is considered to be a base. Sodium and potassium are group 1 elements. Elements in group 1 are very reactive with water. So the products of these reactions are aqueous solutions of a hydroxide and hydrogen gas. Sodium hydroxide and potassium hydroxide are very soluble in water. So the solutions would typically have a bitter taste, feel slippery, but we don't do that. Solutions are caustic, meaning that they are very harsh on your skin. They will cause deep, painful, slow healing wounds if not immediately washed off. Calcium hydroxide and magnesium hydroxide are compounds of group 2 metals. They're not very soluble in water, and they're always very dilute, even when saturated. The low solubility makes the suspension safe to consume for magnesium hydroxide. Some people use the suspension as an antacid. Sodium carbonate and ammonium act as bases when they form aqueous solutions. Neither of these compounds contain hydroxide ions, but they wouldn't be classified by the Arrhenius definition of it, but they are classified by the Bronsted-Lowry definition. Bronsted and Lowry, Bronsted was a Danish chemist and Lowry was an English chemist. They each proposed the same definition for acids and bases. So according to the Bronsted-Lowry theory, an acid is a hydrogen ion donor and the base is a hydrogen ion acceptor. So this theory includes all acids and bases that Arrhenius defined. It also includes some compounds that Arrhenius did not classify as bases. So you can use the Bronsted-Lowry theory to understand why ammonia is a base. So ammonia, when it's dissolved in water, the hydrogen ions are transferred from the water to the ammonia to form ammonium ions and hydroxide ions. Ammonia is a Bronsted-Lowry base because it accepts hydrogen ions, and the water is the acid because it donates the hydrogen ions. So because these things can accept and donate, we can have what are called conjugate acids and bases. So when the temperature of an aqueous solution of ammonia is increased, ammonia gas is released. The NH4 plus reacts with the OH to form more NH3 and H2O. In the reverse reaction, ammonium ions donate hydrogen ions to hydroxide ions. NH4 plus, the donor, is going to act as the Bronsted-Lowry acid, and the OH minus, the acceptor, is going to act as the Bronsted-Lowry base. In essence, the reversible reaction of ammonia and water has 2 acids and 2 bases in it. So a conjugate acid is the ion or molecule formed when a base gains a hydrogen ion. So NH4 is the conjugate acid of the base NH3. A conjugate base, on the other hand, is the ion or molecule that remains after an acid loses a hydrogen ion. So OH minus is going to be the conjugate base of H2O. Conjugate acids are always paired with a base, and conjugate bases are always paired with an acid. So a conjugate acid-base pair consists of 2 ions or molecules related either by the loss or the gain of a hydrogen ion. So the ammonia molecule and ammonium ion are conjugate acid-base pairs. The water molecule and the hydroxide ion are conjugate acid-base pairs as well. You would have to be able to describe or identify what is donating the H plus and what is accepting the H plus. In this reaction, hydrogen chloride is a hydrogen ion donor, and by the definition of Bronsted-Lowry, it's going to be an acid. Water is the hydrogen ion acceptor and a Bronsted-Lowry base. The chloride ion is the conjugate base of the hydrochloric acid, and the hydronium ion is the conjugate acid of the water base. Now let's talk about things that are amphoteric. A substance that can either act as an acid or a base is said to be amphoteric. Water is going to be that main example that we're going to talk about. In the reaction of hydrochloric acid and water, water can accept the proton, therefore it's a base. In the reaction with ammonia and water, water can donate the proton to ammonia to make ammonium, and therefore it's going to act as an acid. Now let's talk about the last definition of acids and bases. Let's talk about Lewis acids and bases. Gilbert Lewis. Lewis should sound familiar because we talked about him when we talked about Lewis dot diagrams. He said that an acid will accept a pair of electrons and a base is going to donate a pair of electrons. So we need to look at the Lewis structure of acids and bases in order to answer these questions. So the Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. A Lewis base is a substance that can donate a pair of electrons to form a covalent bond. So if we were to look at this example between H plus and OH minus, the hydrogen ion donates itself to the hydroxide ion. So the H plus is the Bronsted-Lowry acid and the OH minus is the Bronsted-Lowry base. Now let's consider it and look at the hydroxide ion can bond to the hydrogen ion because it has an unshared pair of electrons. So the OH minus is the Lewis base because it can donate electrons, and the H plus will accept those pairs of electrons, so it's the Lewis acid. A second sample or example of a reaction between a Lewis acid and a Lewis base would be what happens with ammonia when it dissolves in water. So the water are going to be the electron pair acceptors and the Lewis acid, and ammonia is going to be the donor because when you look at ammonia, it has 2 lone pair electrons on that central nitrogen. So let's look at an example problem. So we're going to identify the Lewis acid and the Lewis base in the reaction between ammonia and boron trifluoride. So the biggest thing for you to look at is who has the lone pairs on it that can donate those electrons. So when a Lewis acid reacts with a Lewis base, the base donates a pair of electrons to the acid, and the acid will accept those electrons. So we're going to identify the reactant with the unshared pair of electrons. So you're going to have to draw the structure. So this is what the 2 structures look like. So ammonia has the 2 lone pairs on the nitrogen that it's going to donate to the boron. So ammonia is going to have the electrons to donate and boron's going to have the electrons to accept. So ammonia is going to be the base and the boron trifluoride is going to be the acid. And as always, all of the information on these Google slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbook resources CD and pearsonchem.com. Thank you so much. Have a great night.